And here's the speakers for today. Dan Staples is the Solid Edge Director of Development. He'll be talking about Solid Edge and synchronous technology. Kimball Furniture, represented by Ricardo Espinoza. He's the R&D engineering manager there in Indiana. He'll be talking about his use of synchronous technology and some big plans there at Kimball. And Bob Milletti from Trlby Innovative will talk about, he's the president and founder of his company, and in Connecticut he'll be talking about his use of synchronous technology as well, especially in context of moving from history-based design to synchronous. So with that, let me hand it over to Dan, and Dan will deliver the Solid Edge portion of our presentation today. Dan?
All right, thanks, Mike, and thanks in advance to our two speakers later in the program. Really appreciate you guys joining us. I want to start with sort of the why we do what we do thing. When we go out and talk to folks like the people that are on the phone right now, what are the things you're faced with? What are your business challenges? Excuse me. Time to market is certainly one of those. How do you get more products to market in a faster time? Always pressure in that regard. Another item is the increase in customer demands, and a lot of what I see here, two different things. One is increased demand for variety, so I just need that but a little different. And also increased demand for changes. Not always are these changes anticipated. Customers seem to want all sorts of stuff that we wouldn't have anticipated when we first start the design. As we know, design's fluid. And so that's an area we see people often struggling with. Certainly cost pressures is hitting everyone. I know we're theoretically coming out of this recession, but I don't know if they call it a soft rebound or what the heck it is, but it certainly feels pretty soft to a lot of people. So I would expect most everybody on this call still under some pressure to control or reduce costs. And then finally, really complicated systems and having to learn a complicated system, and particularly if you're coming from 2D, which for its various faults is actually pretty easy to comprehend. And some of the 3D can present challenges in that regard. So that's kind of what we see at the high level of the business challenges. And if you start to dig down a layer below that, and this is a survey done by Aberdeen, who's a really widely respected sort of third party, then you get to the technical reasons why these things are challenging. If you're being asked to improve time to market, I'd say, people from the survey, 39% said they struggle to produce designs quickly enough using whatever tool it is they have, 2D or maybe a history-based system. There's definitely issues there for almost half the folks. Even more so, more than half, when it comes to editing and meeting those customer demands. My customer wants a change, and that change is something I hadn't, anticipated, and folks are struggling with the ability to change things quickly enough and react to those customer requirements in the manner that the customer demands. And then in terms of the cost pressures, I think, a big opportunity here is to be able to reuse data that, repurpose designs from the past or data that you've perhaps been able to acquire elsewhere. And, 44% of the people, so again, almost half said, I'm worried that I can get all that kind of stuff, I just can't repurpose it the way I want. And then finally, learning history, more than 60%, this is again people coming from 2D, have said, well, I get all the benefits of 3D, everybody preaches the benefits, in that regard, it's a lot of the same, but, how do I get there? I can't afford the downtime to make that transition. So these are kind of real factual areas where people are, having some sort of pain in terms of meeting those business challenges. And so our goal with Solid Edge is to help you address those challenges. And in particular, we can address time to market by accelerating design. One of the things we'll talk about, I'm sure, a couple times in this presentation is that design is not a linear process, and it's not the same thing as modeling. If you want to accelerate design, you need to be able to go down multiple blind alleys very quickly, find yourself at the end of the alley, come back, come up with a different approach, and so on. And so we can really help with that with synchronous technology. So that's one area where we'll certainly help you. The other is faster revisions for reacting to those customer demands. As I said, we would like to think our customers make reasonable demands, but on any given day they're going to seem unreasonable. It's something that you hadn't planned for. It's going to cost a lot of time and effort. We can help reduce that time and effort and be able to turn around even unanticipated changes. Being able to reuse things, I think this is a real shining point for Synchronous that we'll talk about today. You can really reduce costs by being able to repurpose your data more effectively. In fact, I think Ricardo's going to talk in a few minutes. I was speaking with him a few months ago about how they're able to repurpose data from 10 or more years ago that had been kind of in cold storage, and being able to repurpose that data could save you just a ton of time. And then finally, this faster adoption. Synchronous works in a really natural way that allows people to adopt it more quickly, and particularly users coming from 2D, they're finding that if they want to get to 3D, and Synchronous is an easier way to get there. So these are 4 different ways we can help you, and I want to dig a little under the covers with respect to that, because I'm an engineer by training, and I know that probably most of the folks on the call here are designers or engineers, and this is all words on paper until such time as you actually dig under the covers and see if it will do your job. And I encourage everybody to do that. What I can provide today is a look under the covers to the technology, and I know engineers and designers are very interested in what makes this thing tick, and I want to explain to you what makes it tick and why it should be important to your business. So I think the first thing to understand is kind of what other alternatives exist, and this is the world prior to the invention of synchronous technology, and largely the world as it exists today, with any other system besides Solid Edge. And it's really these 2 separate worlds, as you see the brick wall between them. We as an industry, the CAD industry, have presented to you technologies and said, well, here's history-based modeling and it works in a certain way. And then there's history-free modeling and it works in a very different way. And there are these 2 things, but they are not the same, they are not even similar, and they're not integrated in any way. And there have more recently been attempts by a variety of companies to do some sort of what I call loose integration, throwing things over the brick wall, but nothing at all like synchronous technology in terms of the ability to address the needs of both of these areas. And so to understand those a little bit, I put together a quick backgrounder on each of the technologies. I expect most people on this call are more familiar with history-based, but I think Solid Edge still does history-based as well in certain areas, and it's something that we're all kind of familiar with, but we kind of forget some of the downsides of it. So I want to be clear on exactly how it works and what's the good and the bad of it. So whenever you create a history-based model, it creates this recipe of steps, which is very valuable in that it captures the design intent. So you have the sketch profile, it's got dimensions, it's got constraints, all that stuff is captured, and it will replay those same steps to achieve a slightly different shape when you edit a dimension, something like that. The thing we often lose sight of is the downside to that approach, and that is that any edit requires a replay of all subsequent steps. Now we all say, yeah, of course it does, but that's just because we're used to it. It's certainly not necessary to do so. If you have a hole on one end of your part that is feature 2, and you have a hole on the other end of your part that's feature 502, there's really no reason why editing feature 2 should recompute feature 502 and everything in between. They're not related to each other in any way. And so that's really kind of a nonsensical thing that we've foisted on the community with history-based modeling. And then the other thing that I think we tend to forget is, well, or maybe we don't, we hit this a lot, is how it was created is how it must be edited. And so you end up spending a lot of time in the initial stages of your design, not designing, but instead planning how you will CADify your model, and that's just lost time. And then finally, it's not very effective at editing imported data because, as we know, transferring history trees between systems doesn't exist, and therefore it makes it very hard to edit. So just to give a quickie on how this works, I think many of you on the call know this. If you start at the bottom of the screen and the boss says, make this oval bigger, you end up having to roll it back to the top of the tree here where the oval was instantiated, and this is a real part. Edit that, and then regenerate every feature below it whether they changed or didn't change. And so that's the good and the bad of history-based modeling. If we then look at history-free systems, basically there is no recipe or history tree, so it is just the body itself, and you do all the editing. But typically in these systems, it's all done through a push-me, pull-you interface, so that's what I call it, where it can be precise, but it's not necessarily a dimension-driven system. And so what you see is it's very fast and flexible because you don't have to recompute the recipe or regenerate the recipe. But they tend to be, and we looked at a lot of these systems before we built synchronous technology, and the places where these systems tend to fall over is being very feature-based. They're not very feature-based. It's hard to capture and maintain that design intent, and they tend to be significantly non-dimensional. You tend to do a lot more push-me, pull-you, and less, I want to set all these dimensions to particular values and have them respected. And so that's kind of the way history-free kind of system would work. Now, the reason this is relevant to you guys is what it ends up doing is kind of forcing you into a camp, right? You're going to have to decide, do I more fit profile A or profile B? Profile A being history-based, I've got these well-defined problems, my dimensions are well-known, my changes are usually fairly minor, and so on. And so this parametric, dimension-driven, people fall into this category of choose a history-based system if they most closely identify with those set of statements. Now, if you go over to history-free, people who fall into this category typically say, well, my design changes all the time, my design needs are very fluid, I don't know what changes are going to be asked of me, and so you end up in this direct manipulation history-free modeling kind of place. Well, that's all well and good, but that's just because we as a CAD industry have pushed to you these two technologies, and you have to decide one or the other, even though you might not be able to identify with all of these statements, or you might identify with statements that cross the line. And so I think that's the big bad secret is that you, the user, is not one-dimensional. You don't fit in either of these two camps, right? So what tends to be true for almost everybody, I think, is, as we said, design is not a linear process. And so at the early part of design, you want to try out different things. You have very fluid design needs. But at some point, you get pretty locked down. You're like, I need this to stay this way. I need that to stay that way. And so you have the very well-defined dimensions and behaviors. And then finally, we can't certainly make the presumption that you're just always designing all your own stuff. There's lots of stuff to integrate from other systems. So I think this is the more realistic profile of most users. And so as a result, that's what we developed with synchronous technology. So if you think about history-based on the left, I want to be very clear. I mean, like I say, Solid Edge was purely a history-based system for, 13, 14 years maybe. Very good things in history-based modeling. It's very automated. You make a change, lots of good stuff happens. It's very dimension-driven, which is the way engineers like to think, and designers. And it's feature-based. Those are all really good things, right? Then outside the scope of that are some not-so-good things, right? There's the pre-planning that's required, the pain that if you have to change something you hadn't planned for. Large feature models can take a long time to regenerate. So those are some of the not-so-good things. If we go to the right-hand side of the equation, we see that history-free modeling also has some really good things. It's very direct. People love the directness. I just tell it, I want to do this, and it does that kind of thing, and it scales very well on many featured parts, and it's very flexible. But as I said before, not very good at doing feature-based modeling. Dimension-driven is usually suffered, so on. So, the pluses and the minuses to each of these technologies. And so what we did with Synchronous was to say, well, why should I have to go into one camp or the other? Why can't I take the good dimension-driven, feature-based concepts and scale that well on, many featured parts in a direct way? And the answer is, yeah, you can do that. You just have to invest a lot in technology to make it happen. And so we created concepts like procedural features, which are like little history nuggets in the middle of a non-history-based tree. Live rules that keep that design intent even without having to store a lot of data, and driving 3D dimensions between any 2 points, and so on. So the answer is you can have the best of both worlds, but you need to invest a lot in the technology to do so. And I'll come back to in just a second how is it that we're able to invest in that technology and make it happen. But before I do that, I'm going to show you just a little clip to kind of compare the two. And this particular clip revolves around the notion that we're going to do the exact same change, first in ordered or history-based, and then do the exact same change in synchronous, and just give you an opportunity to see and compare and contrast the two.
If you've used a traditional 3D CAD system, you're familiar with performance issues due to model regenerations. Let's look at a typical engineering change order scenario and see how much faster edits can be made using Solid Edge with synchronous technology. Most change orders begin with documenting a set of requirements. View and Markup in Solid Edge allows you to efficiently mark up assemblies, parts, and drawings, which can be emailed using a lightweight PCF file. Recipients of the file can view the changes in Express Review, a free viewer that can be downloaded today. You can package all types of documents such as requirements documents, spreadsheets, drawings, and even images. After reviewing the requirements in this engineering change order, it's time to make the edits. Before we show you just how fast Solid Edge with synchronous technology is, let's refresh your memory on what it takes to make changes in a traditional 3D CAD system. We'll start with this console cutout. Feature edits in a traditional CAD entail a delete and recreate process, so during any edit the model rolls back, deleting all subsequent features. Only features built to accommodate future changes will update correctly. We got lucky here as this feature was constrained to keep the cutout in the correct position. This simple edit took over 15 seconds to make, but larger models can take much longer. We'll make similar edits to the frame and hanger clearance pockets. Once the edit is complete, all remaining features must regenerate, even operations that were not affected by the change. This rebuild process is a common source for model failures because subtle changes can cause severe and unexpected results. The behavior of this 20-year-old architecture is what most people consider the norm. Let's now make a more complex edit to the tank profile. Since this change wasn't something the designer planned for, the results will be unpredictable. Once the edit is complete, notice how many features failed. The original designer didn't build the model in anticipation of such a change, and this is a classic problem found with traditional CAD technology. During the regeneration process, subsequent features are bound to break. Imagine the number of steps required to fix all these features. Creating models flexible to changes in a history-based system takes a tremendous amount of pre-planning during the construction phase so that edits will give the correct results. As we see here, the model wasn't built to accommodate even the simplest changes, and if you did not originally create the part, you have to untangle someone else's mess before you start. Let's now see how Solid Edge with synchronous technology eliminates these issues. We'll make the same changes in Solid Edge so comparisons between the technologies can be seen. An initial difference is how models are edited directly. With this approach, changes are made directly to the geometry so you can edit in the most convenient way. Simply drag a face or add 3D driving dimensions. Remember, the edits with traditional CAD took a while to recalculate and lots of additional time was required to fix failed features. But using Solid Edge with synchronous technology, these edits are done in just a few seconds. The edits you see here are happening in real time. When you need to make fast, reliable changes, there really is no better system than Solid Edge with synchronous technology, even with parts coming from other systems.
Okay, so hopefully you're able to see in that video some of the difference between the technologies and the productivity that Synchronous brings to the table. I think one of the obvious questions is, well, how exactly then is it that Solid Edge has this technologies and others don't? And so I think I can most easily explain that to you in terms of the way different technology stacks work. And so when we talk about a software stack, it's how you build up a product that you deliver to an end user. So if we take just an example, so SolidWorks, at the very base of the technology stack is the thing that does the geometry modeling, the thing that, when you create a cutout, a protrusion, a hole, any of that stuff, pretty tough, difficult math down there. That's all done by a piece of software called Parasolid. There's another piece of the software that deals with constraints. When I want to put together an assembly and I want to assemble together parts and I align some and mate some and so on, how does that solve into a cohesive whole? That's done with a technology called D-Cube. Now, these are technologies that we actually write as part of Siemens and are provided to Dassault SolidWorks. Now, what they do with those technologies is to wire them together with all the user interface and a variety of other glue. And I want to be clear, I mean, Dassault SolidWorks is a very good product with a lot of very smart people, and they wire it together in ways that are valuable to you as an end user, but it's basically taking the technology which we provide, wiring that together to create the various commands that are provided as the end user CAD product. The reason I want to explain this to you is to contrast that with the Solid Edge technology stack. So in this particular case, we own all the technologies top to bottom. So Parasolid, the geometry modeler, and D-Cube, as I said, are written by us. And so what that means is that as a result of that, Synchronous technology is really a marriage of those two in a very interesting and unique way with a lot of unique concepts. And it's really enabled by the fact that owning the entire technology stack top to bottom, we have unique understanding, unique relationships, and so on that allow us to create this synchronous technology layer. And then, of course, on top of that, we build Solid Edge, where we then wire the synchronous technology in with the rest of Solid Edge to deliver this to you. So I think this unique combination of the two technologies and the fact that we own the stack from top to bottom is largely what allows us to bring this technology to you where no one else can. And so whereas the lowest layer of that stack, the Parasolid and D-Cubed, we made a decision many years ago, probably 20 years ago as a company, to play that level, what we call level playing field. We provide those technologies to our competitors, such as Dassault SolidWorks, and that's the level playing field. With Synchronous technology, we made a strategic decision many years ago. That's not going to be a level playing field product, so that's not a technology that they can source from us, nor can anybody else. And so as a result, the things you'll see in Synchronous technology are in fact unique to Solid Edge and our NX product lines, and something that you'll not be able to source really anywhere else in the industry. And so that's kind of the magic behind Synchronous and why we're able to bring that to market and really help you with these issues. I do want to go to another video here. I saw there were people from Inventor, SolidWorks, and so on the call. There's a really unique technology that we put in place just for that purpose, and that's the ability to take solid models from those systems, bring them into Solid Edge, and then take the dimensions from the drawing and drive the model with the dimensions from the drawing, even though this came from a foreign CAD system. So take a look.
Solid Edge ST3 lets you preserve design intent from imported 2D drawings to imported 3D models to improve data reuse. Let's start the process by reading a 3D part and associated 2D drawing from another system. Solid Edge's migration wizard ensures drawings look the same in Solid Edge as they did in the original system, including layers, line styles, color drawing scales, and more. Using the Create 3D command in Solid Edge ST3, manufacturing dimensions from the 2D drawing are automatically added to the imported 3D model. These manufacturing dimensions are key when making changes. The goal of the designer is to alter the dimensions directly and not indirect sketch dimensions used during the modeling process. Prior to Synchronous technology, imported models had to be redesigned to allow edits, but with these new enhancements, designers can make the changes as defined in the 2D drawing. Once the process is complete, the 3D driving dimensions can be edited. Unlike feature dimensions that control parts of a model, designers can now control what really matters, such as distance between holes and overall size across multiple features. The ability to edit imported models with precise dimensional control is made possible only with Synchronous technology. During edits, design intent lost in translation is found and maintained with live rules. This keeps designers from having to remodel imported parts even when simple edits are needed. A similar behavior is seen when the base plate thickness is adjusted. Other coplanar faces are maintained, keeping the designer from making two edits. You can add dimensions from other drawing views all at once or at any time, depending on design needs. Here, the dimensions from an auxiliary view will be transferred to 3D, ensuring the positions of holes along the angled face are kept using the dimensions defined in 2D. Even intent established in detail views can be transferred into 3D. Regardless of drawing view scale, dimensions can be moved from 2D to 3D and are ready for edits. Watch as a precise change is made. Finally, fully associative solid edge drawings can be easily generated and manufacturing dimensions can be retrieved, ensuring design intent is maintained throughout. This new capability within Solid Edge ST3 helps designers reuse more 3D data from customers and suppliers, which help reduce overall engineering costs.
All right, so I hope you're able to see then in that video something that I think is really rather amazing, something that 4 or 5 years ago, if someone said that exists, I would have called them a liar. The ability to marry a 3D model with the capability to inject the dimensions into it from a foreign system and drive it. So I just want to, kind of sum things up here from my point of view and get some customer perspectives. I told you that we were going to help you accelerate your design for faster time to market, and I hope that I've given you some idea of how that's true. Being able to recognize that in fact design is not a linear process, and so you need to be able to make blind alleys, head down blind alleys, and head back out, and be able to try different things, but still while controlling it very precisely. You certainly need to be able to make those revisions that your customers need, and the thing is, the design intent need not be locked in stone. You need to be able to keep or change intent as required. And because the model generation, there is no such thing as model regeneration, it's an extremely fast process. Being able to reuse and repurpose that imported data, I think, is very key. Repurposing data perhaps even from a long time ago and taking those potentially dumb solids and making them smart and usable. And then finally, if you're coming from 2D, you don't need to be worried about the system and how long it will take you to learn. You'll have very little downtime as you learn Solid Edge with Synchronous, because you really get the 3D power with the 2D simplicity. With that, I'm going to turn it back to Mike and let him introduce our other guests. Mike?
Okay, great. Thank you, Dan. Yes, I would like to introduce to you Ricardo Espinoza from Kimball Furniture Group. He's the R&D Engineering Services Manager there. And Ricardo, the floor is yours.
Okay, thank you. I'm going to start to talking a little bit about my company and then why we decide to go Synchronous. Kimball International provides engineering and manufacturing services for electronic components in office and hospitality furniture under the brands Kimball Office, National Office Furniture, and Kimball Hospitality. Kimball has been using CAD technologies since the 80s. In the early 90s, we moved to ideas, and in 2004 to Solid Edge. Since then, and until recently, we have been using history-based CAD technologies. While we moved to Solid Edge, even that we got a better CAD system, we left behind thousands of legacy files in ideas format. This older data created using ideas remained difficult to use, but is still very important. This presentation was originally created for our own engineering management team to show them why we decided to go Synchronous. What are the advantages of Synchronous technology for Kimball? What are the benefits, the constraints, the challenges, and the opportunities? With some modifications, mostly to reduce the original presentation from 1 hour to 15 minutes and to replace heavy videos for lighter slides, to make sure that they work in this webinar, this presentation will give you an idea of what is Synchronous technology, and what you should expecting from it from a user perspective. We have more than 50 design engineers using the system. We use all kinds of materials, shapes, and manufacturing process in assemblies with hundreds of parts and configurations. This is what we are doing and what are we planning to do to get most of this technology for all of our products and processes, and how to take advantage of this technology for furniture, wooden materials, and complex seating. Kimball faces many business challenges, including a rapid, challenging office environment, new products with more features, and of course, cost pressure. Changes in the office environment include better work interaction and networking, new communication technologies, integrating in electronics and the furniture and more modular furniture. All this places new demands on engineering. In addition, as you know, resources are always a challenge. Being able to use all the legacy data that we have from ideas and using our vendors' data without costing translation is in itself a very good reason to update, but we expect more. We are eliminating the tedious tasks in history-based CAD, giving our designers more freedom to create, make changes on the fly, just clicking and dragging with no worries on unexpected results, and that's helping us to save a lot of time. And it's more fun. Fun means productivity for our engineering teams. I show our management team two simple videos of what synchronous technology is and why it will make a difference for us. I'm not showing these videos here due to time and bandwidth constraints. However, I will talk about them. I'll show them how we can create complex shapes in seconds using regions, like this gear. I draw a square and a circle, then I made 4 rotated copies of the square, then I pulled the resulting regions, creating the final extruded shape in a very short time. In the second video, I show how to create a basic 3D model of a wood chair from a napkin sketch. Using the technique that you just showed in the previous video, we just copying the two-dimensional information in that napkin, and then we create a simple chair, and we have time to explore all the different options. Synchronous technology is still evolving. Siemens has been adding hundreds of user requests to each new release, and I believe that ST4 is mature enough for Kimball to implement it now. All our case goods, machined parts, sheet metal parts, and assemblies can be done or edited now in synchronous technology. And that eliminates a lot of tedious tasks. It is especially powerful in creating specials from existing components. Most wood chairs and many components for non-wood chairs can also be handled in synchronous technology. However, complicated surfaces like those in seats, backs, and armrests are not a very good fit for synchronous technology. However, using both technologies in the same environment, in the same part, solves the problem. We can do all features required by the design intent in synchronous technology and cosmetic and manufacturing features like rounds and drafts and complex surfaces in order. We know Siemens is still working on making synchronous technology more powerful, so we hope that in the future versions we'll be able to handle all these complex components in the synchronous environment. What are the reactions to new software? Well, this is not new software, but in some way it's a new way to work with CAD models. Ironically, it's the way that I learned when I was a kid. When I started working exploring synchronous technology 2 years ago, I was not sure about it. It changed almost everything I learned in the last 20 years about good CAD practices. After some training and a lot of practice, I started forgetting all these computer-driven techniques and relearning how to go simple. When I understood that history is completely irrelevant in synchronous technology, that was my aha moment. I started liking it. Now, I'm sure that our engineers and designers could be a lot more productive. We are rediscovering how fun is product design. This is not the first time that we made a big change in our engineering information system. As I mentioned before, in 2004, we migrated from ideas to solid edge. So we know how hard it is to do that. It is a CAD manager's nightmare. So it is really a CAD manager's nightmare, or is we're just overreacting to the natural resistance to change? Well, it is. It's a real CAD manager's nightmare. I'm telling you. Training 50 advanced engineers, 30 casual users, implementing new standards and new best practices, dealing with the learning curve for weeks or maybe months, and dealing with all the natural resistance to change It's a lot to do. So does going synchronous work all this? We believe it does. The improved productivity, the fact that we can use legacy ideas and vendors' data directly are really big. So once we learn what synchronous technology is and understand these four basic concepts, that history is irrelevant, that the steering wheel is the main and the most used tool for 2D and 3D geometry manipulation, light rules and relationships are ways to get there faster, and we have full control of them and working in the assembly, then we know that it will work. Last spring, we decided to go synchronous. So we choose a group of super users. We select engineers from all our divisions to start a pilot program with synchronous technology. After a successful result, we decide to migrate the rest of the company. Now, we can open, without any preparation, files from other CAD systems, including all these legacy files that we have from ideas, files from SolidWorks from our external designers, and any other files from suppliers and customers. Changing existing geometry is a lot easier and faster. Learning synchronous technology is a lot easier for users with no CAD experience. And we're planning to implement in the following months new functionality that was not available before synchronous technology. We estimate that it will facilitate our work even more. We are planning to implement new features like system libraries, smart templates, and simulation. These are, in my experience, the four key concepts that you have to understand and to implement synchronous technology successful and improve your productivity. Learn how to manipulate the steering wheel. Full understand life rules and relationships. Remember that history is irrelevant, that how to get there is not important, only the final result. And working in the assembly. Remember that parts are not islands. Use the assembly reference to create or edit your parts. No need to open, change, close, reopen, change again, close, and do this for hours. In synchronous technology, the design intent is inherent to the model. You create once and you can edit forever. Edit is not bound to any creation methods. One of my favorite parts in synchronous technology is the ability to create and or edit parts in the assembly context. You really save hours of working directly in your parts using the assembly reference instead of the open, edit, close approach in order. Many times our engineers decide to start from scratch instead of using existing parts because recomputing ordering parts take a long time in complicated models. Users spend a lot of time trying to decode what order intent. If you are not the originator of the file, it takes a long time and sometimes it's impossible to understand what some other people did with this file. And complicated edits to move parts may affect the fit in the assembly. So if you make some change downstream and it fails, you're going to probably spend hours just to redoing the whole assembly. I'm going to show you here a real situation. We needed a new credenza with 3 doors. All features, including style and color, match an existing product. So instead of starting from scratch, as we used to do with older technologies, we use an existing credenza with 2 doors and 4 drawers. But we have a problem. This product was designed 15 years ago. All data is in ideas format. Well, with synchronous technology, it's not a problem anymore. We can reuse all this legacy data immediately. However, when I tried to open my assembly, I found one part missing. I had the drawing, but the solid was gone. No problem. Again, with synchronous technology, we use the same technique that Dan shows in the last video to create the missing parts from the existing 2D geometry in minutes. Then, using synchronous technology and working in the assembly context, I created the new assembly in 10 minutes. Hard to believe, when I know that with older technology it will take 3 or 4 hours. Originally, this was a video showing in real time the conversion process. But for this presentation, due to time and bandwidth restrictions, I will use a series of screenshots. Keep track of the stopwatch in the upper right corner. In this credenza, an important model from ideas, we start with that, and then we delete all the features that we don't need. We can work directly on each part without opening those components. We delete or adapt more of these features. We delete more parts, including hardware. We have a lot of small components that needs to be removed from the existing credenza. Then we move the existing doors section to the right without even knowing the dimensions. We just use the steering wheel, one starting point and one existing reference point to do the whole moving. Then we adjust the door size. The new credenza requires bigger doors, so we just adapt the existing doors, growing them with click and drag. And then we move the doors to the right position. We have inner shelves also, so we have to enlarge those shelves to match the new dimension. And again, we didn't use any dimensions. We just click and drag using synchronous technology in the assembly. The hardware is adjust using predefined rules. Then we add an additional door. We adjust the size of the credenza. And then we have to change the size of some components. We use synchronous technology, assembly relationships, and moving only one dimension, we adjust all of those components at the same time. We add more shelves to the right side. We adjust the size of these new shelves. And finally, we adjust the remaining hardware. And done. We finish something that usually takes 3 to 4 hours in less than 10 minutes. Summarizing this experience, we estimate that we will improve our productivity after the learning curve period, and we estimate that we can go from a little more than 7 hours to a little more than 1 hour working in similar assemblies. The challenge is now make this possible in the whole company. So thank you for your attention, and we'll go back to you, Mike.
Great. Thanks, Ricardo. Very, very impressive. Thank you for sharing that with us. We've got about 15 minutes left, and I wanted to hand it over to Bob Milletti from Trlby Innovative in Connecticut, and he's going to talk a little bit about what he's doing with synchronous technology. Bob?
Well, thank you, Mike. Again, sorry for the technical difficulty. As you can see from the first slide, I'm a Winosaurus. I'm an old history-based kind of 3D parametric CAD guy. Been working with Solid Edge for about 12 years now. And I had a real hard time moving over to synchronous technology, but I learned to find out that it was mostly me and my approach to it that was causing the difficulty. Let me give you a little bit background. We're a design consultancy firm, mostly focused in R&D and do development work for these list of companies that you see up on the screen. These are some of the products that I've worked on over the years, everything from custom outdoor furniture to custom machinery. Most of the custom machinery is focused around the heat sealing of plastics. Recently we had a project, and we're still actually working on this project, where we are retrofitting a bundler system for a paper mill. They have 26 of these paper towel bundlers, and this actually puts the overwrap around paper towels and paper tissues. The specific thing I'm going to talk about is one of the blow-off plates and that required air deflection plates and air channels to blow cold air onto the process after we've done the heat sealing. What the original installation we had in there for testing had a few small air leaks, and we needed more airflow across the web. So in History Base, I was very comfortable with how to do this. I would go in and look at my sketches, which were the basis for all the parts. And in this case, I show you the top outline of the part. And then the second picture down is the air channels. And then finally are the slots, the 5 slots that basically hold the product, hold the plate in place and allow it to function, go up and down. So when doing this kind of editing, because of the ordered nature of history, I would move the first part and then move myself down. And this was all pretty straightforward, mostly either using move commands or actually doing dimensional changes. Very effective, but tedious because each feature had to be done individually. That was easy, but coming to the air channels, it got a little bit goofy and a little bit difficult. When I moved some of the areas, I would end up with some issues. When I moved to sync, I actually found it at first very difficult, but I realized sync was smarter than I was at this. And moving these oval slots was a little bit difficult because of user intent. And actually there was more user intent in my part than I gave credit for. And sync was smart enough to see this. So how I solved this was I couldn't use the user intent that sync was requiring me to use, but I was able to copy the sketch or the part features, because it was an original solid edge part, very effectively, and re-put in those slots and then have them completely become associative to the Synchronous part. This was a very fast and very easy way to do it, and it turned out to be very successful. I was able to redesign the air channels and reposition these oval slots so that we didn't have the air leaks anymore. So within about 10 minutes, I was able to change this plate completely by using Synchronous technology and actually have the parts made relatively fast. It was very successful and really opened my eyes to how effective Synchronous technology could be. But as Ricardo mentioned, it's in the assembly environment that is really a lot of fun to watch Synchronous move. What you see here is an assembly of a bouncer chair. This is a rocker chair. And my customer was interested in looking at the different pitches and changes of the seat system so that he could sort of, from an aesthetic standpoint, look. And although I don't have a video here, but this all can be done in real time, where we could change the pitch of the seat, how far back it's at, and change the height, change all of these details. But the pictures in the middle row is really where Synchronous shines. I was able to attach the end of the arm to the coplanar of the back, and as I changed that back angle relative to the seat angle, that actually flowed with it. I didn't have to go back and edit subsequent parts or go back and redo everything. Just from the assembly environment, I was able to edit all of these parts. So whether I was changing the height or changing, the backrest, it all flowed right through assembly. So it was sort of a struggle at first, but once I opened my mind to it, I really found myself, becoming a Tyrannosaurus, where I opened my mind and I found that Synchronous was really, really intuitive and smart, and I find it very, very enjoyable to work with now. So thank you very much for your time.
Great, thank you. Thank you, Bob, and thank you, Ricardo, and thank you, Dan.